So this is in continuation to our previous lecture where we understood till the 2D arrangement of particles. Right now we will understand the 3D arrangement of particles, right, where we have already discussed in 3D arrangement how we can build a 3D arrangement, right, from this square close packing. And to build a 3D arrangement, right, if to build a 3D arrangement, what we need is we need a where we in 3D arrangement we stack the similar layer, right, of spheres onto the first layer. We take the second layer and stack or put it on the first layer, right. So in square close packing, what we do is when we put the second layer onto this first layer, right, the spheres of the second layer will be aligned with the spheres in the first layer. I'll read: the spheres in the second layer that we stack onto the first layer, right, will coincide with the spheres onto the first layer. That is, the spheres in the second layer will be exactly above the spheres of the first layer, right. And the voids, we know that the voids are these empty spaces. The voids in the second layer would also be on the voids on the first layer, right. So what we get is this simple cubic lattice with this kind of arrangement, right, in 3 dimensions. And this simple cubic lattice have primitive cubic unit cell that has particles only at the corners. And this is the kind of, and this is the simple cubic lattice that we get, right. Now let's see how we can build a 3D arrangement, right, 3D arrangement using this hexagonal close packing of 2 dimensions. Now what we do is, let's first understand little about voids in this hexagonal close packing. We have 2 kinds of voids in hexagonal close packing. One is this, these voids are triangular shape, right. These voids are empty spaces, hollows, right. These are triangular shaped voids. One is this, the other is this, right, in HCP. These are triangular voids. One of the voids, right, these are triangular voids in which the apex of the triangle is pointing upwards, and these are the second kind of voids in HCP arrangement in which the apex of the triangle is pointing downwards, right. So when we build the second layer onto this first layer of HCP, what we do is the particles in the second layer will come onto these voids, right, and we will put the particles on one kind of void. Either we put the particles of the second row onto these voids which are pointing downwards, or we put the spheres in the second row, in the second layer onto these voids that are pointing upwards. So if, let's say, this is the arrangement that we get, wherein the spheres in the second layer is formed by putting the spheres onto these voids which are pointing downwards. You can see this. These are the voids, right, wherein the spheres are put onto these voids, right. So these voids, the voids that are pointing upwards, are left unoccupied, right. So only one kind of voids would be occupied in this arrangement, the other would be left unoccupied, right, because there is no space, right. So we cannot put spheres onto the second void, right. So this is your 3D arrangement. Now let's see if we want to build the fourth layer, the third layer, the third layer onto these arrangement, how we can do this, right. Now if you look at this arrangement, in order to build third layer, again we have to put the spheres in the third layer, or the particles in the third layer would be arranged onto these voids only. So let's see the voids that are created when we build the second layer. First is these voids, right, these voids which are the voids of the first layer, and the second type of voids that are formed from the second layer, which is these voids, right. Let's say these are D, right, and these are C type of voids, right. And so these are 2 types of voids. So when we will build the third layer, right, these voids or these voids, what we will do is, let's say this is the D, right, and these are C, unoccupied voids of the first layer. This we say is an A type arrangement. This is a different type of arrangement in the second layer, right? So this is your B type arrangement, right? AB. This is your AB type arrangement. Now let's see. So this arrangement of two layers in 3 dimensions is your AB arrangement. AB arrangement. Right? Now when the third layer is added, we know that we have two types of voids, right? One belong to the first layer, as I said, and the second belong to the second layer, right? Now two voids, two ways to form the third layer, right? Now from this 3D arrangement, right? From this arrangement, from these two voids, we can do two things. Either we put the spheres onto these voids, or we put onto these voids. Let me represent it with different color so that it is visible. Right? This is the one kind of void that we have, right? Which is the void on the second layer, right? And these are the other kind of voids. Second kind of void that we have, these are the voids on the first layer. So what we will do now is, if we will put the spheres onto these voids which are the voids in the second layer, right, the sphere will coincide with the layers with the first layer, right? If I am putting the layers onto this void, the spheres are coinciding with the first layer. That is, this, if I put the sphere onto this void, it will align with the first layer, with these middle. If you look at this, the middle row, if I put the sphere onto this void, it will align with the spheres in the first layer, right? So the kind of arrangement that we will get is AB, right? This is again ABA arrangement that we will get, right? Because the third layer is the same as the first layer, right? And this arrangement that we will get is your HCP arrangement, right? We have called these voids are D voids. Nice place to build the third layer. To build third layer, put spheres on void D, right, onto these voids, right? Or the second way you can do this is put spheres on void C, which are the voids in the first layer, right? So if I put, as I said, if I put the sphere onto these void, the D1, the third layer will coincide with the first layer, right? So here third layer will coincide with the first layer, right? And if I put the spheres onto the other void, we get a new type of layer, right? So this here I get this kind of arrangement, A, B, and third will coincide with the first, the A type of layer, ABA arrangement, right? And if I put the sphere onto these voids of first layer, I get a new type of layer which is C layer. I put the sphere on void C. This sphere, this is a new type of layer because this does not coincide with either A, right, or with either B. This is a new type of layer, C layer. Like in the previous case, when I put the sphere on the voids D, which are the voids of the second layer, it coincided with the spheres in the first layer. So that is why we said it's A type layer, right? So third layer is A type layer in this case, ABA arrangement. Here, the layer that I get when I place the spheres on the C void, right? This C void, voids of first layer, I get a new type of layer which is C layer, right? So arrangement is ABC, ABC, right? So this is little confusing, but if you will just consider and look at it, and if you just concentrate on it, you'll get it. It's easy, right? And now in this case, right, I get a new layer when I put the spheres onto this layer. This is the third layer, right? This new type of layer, third layer. Now if I form a fourth layer, right, with this kind of arrangement, the fourth layer that I get will coincide with the first layer, right, will be aligned with the first layer, right? So that would be for the fourth layer, the arrangement would be ABCA, right, ABCA. This fourth layer will again coincide with the first layer, right? And this is your HCP arrangement again. Sorry, this is your CCP arrangement, and this is your HCP arrangement, right? When you put the spheres on void D, this is your, what we get is your, HCP arrangement, hexagonal close packing arrangement, and this is your centered cubic packing, CCP, centered cubic packing. CCP stands for centered cubic packing. An example is for ABA arrangement, it's magnesium, zinc, beryllium, right? Magnesium, zinc, beryllium will crystallize with HCP arrangement, right? It will crystallize in HCP structure. These elements crystallize in HCP structure, right? Similarly, the CCP symmetry that we get on putting the spheres on void C, right? The arrangement is ABCA, right? Spheres at center, right? In this kind of arrangement, right? This is the structure that we get with this kind of arrangement is your FCC. We have one sphere or one particle at the center of every face. So this is your FCC arrangement, right? Face centered, face cubic, face centered cubic. An example for this is iron, copper, nickel, right? Example is iron, copper, nickel. These are the example of crystals that crystallize in this CCP arrangement, right, or CCP structures. Now the two kind of structures or arrangements that we get, which is HCP and CCP, both these are efficient way of, both are equally efficient packaging and equally economical, right? In both the arrangements, 74% of available volume is occupied. So here the packaging efficiency, that the one that we talked about at the previous or in the beginning of previous lecture, the packaging efficiency is 74% here, and here also the packing efficiency is your 74%, right? So these are two arrangements, HCP and CCP. There is also a third kind of arrangement. That third arrangement is your, so here when we said 74% is your packing efficiency, that means 74% of the space is occupied by these spheres, and the rest 26% is your empty space. So here 26% is empty space with this HCP and CCP structures, or HCCP and HCP arrangement of particles. Now there is another type of arrangement we have. You know that there is one more arrangement which is your body centered, BCP, body centered packaging, right? Body centered arrangement of particles, BCC we call it, right? So in BCC we have metals, soft metals like sodium, potassium, rubidium, right? Particles like sodium, potassium, we have another kind of arrangement which is your BCP, body centered, right? Body centered, we are already aware of this type of arrangement. Sorry, this is not BCP, sorry, not BCP, this is BCC, body centered cubic, right? An example of metals that crystallize with this arrangement, body centered cubic, is your sodium, potassium, right? Lithium, these are the ion, rubidium also, I guess, yeah, rubidium, right? These are example of solids that crystallize with BCC structure, right? BCC structure. Notice one thing, that magnesium, zinc, beryllium, iron, copper, nickel, right? And we said that this is more efficient, 74% of space is occupied, but this BCC is not much efficient compared to the above HCP and CCP, right? Because in this case 32%, here 26% is empty space, here 32% is empty space, that means only 68% packaging efficiency we have with BCC. So packaging efficiency with BCC is less, 68%. We have more empty space. So these metals are not as denser as the solids that crystallize with CCP and HCP arrangements, right? We know that sodium and potassium, they are soft metals which can be cut with a knife, whereas you cannot cut iron, copper or nickel. They are very hard metals. We know now the reason, because these have these kind of arrangements, right? HCP and BCP arrangement of particles that have more packaging efficiency and less empty space, whereas metals like sodium, potassium, lithium have crystallizes in BCC arrangement that has less packaging efficiency compared to these, and less and more empty space, right? So these are soft metals, these are tough metals, right? So just go through this, just understand how we build the second layer, right, or the two-dimensional structure from this one-dimensional structure. One-dimensional structure is we place these spheres side by side. Then there are two types of arrangements to build the 2D, right, 2D structures. One is you align the spheres in the second row, and the subsequent rows would be aligned with the first row, right? That is, one, the spheres in the second and subsequent rows would be exactly below the spheres in the previous row. Previous row, I mean the spheres in the second row would exactly be below in the first row, right? So this kind of arrangement you get square close packing. Similarly, the second type of arrangement is when you can put the spheres in these depressions. So this kind of arrangement you get. Coordination number of this is higher compared to this, so this is more efficient way of packaging, or this is more stable because here the coordination number is high, and the packaging efficiency of this HCP, hexagonal close packing, is 60.4% compared to this 52.4. So this is more efficient way. Similarly, when we build the third layer, remember that when we build the third layer, we'll put the spheres on these voids. right? So in this arrangement we have two types of voids with triangle, with the apex of the triangle pointing upward and downward, right? So we will put the spheres in the third layer onto these voids, and this is the structure that I get, right? So when you build this is the second layer that we have built, right? Now if you want to build the third layer, I can put the spheres onto these voids, which are voids of the second layer, or onto these voids, which are voids of the first layer. So again I get two kind of structures, HCP and CCP, right? Both these are efficient way of packaging because we have packaging efficiency same in both the cases, 74%, right? Whereas there is third type of arrangement, BCC, right, that has less packaging efficiency and more empty space. So metals are soft in this case with this arrangement, with BCC kind of arrangement, right? And when we made this 3D structure, right, from this square close packing, when we put the similar layer onto this layer, what we get is your simple cubic lattice, which is again not a good way of, or which is not the efficient way of packaging again, right? And you can see that in this arrangement we have coordination number 4, here we have coordination number 6, so this is more efficient way. Similarly, if we talk about these HCP and CCP, here we have coordination number 12, right? You can see this in 2 dimensions. Any sphere, this is in touch with 1, 2, 3, right? These 3 spheres and these 3 spheres, so 6 are here. Now 3 are below the layer, 3 are above the layer, right? So we have coordination number 12, that is any sphere is in direct contact with 12 other spheres. Similarly, if we talk about the coordination number of BCC, the coordination number for BCC is 8, right? So here the coordination number for BCC for this one is 8. That is why this is not efficient compared to this. Here coordination number is on higher side, right? So I hope all this is clear to you. Thanks.